Hello everyone. So today we shall see about the minimum phase systems. So in the last lecture we studied about the all pass systems and we also see a couple of properties such that the phase contributed by the all pass rational function is always less than or equal to 0 for omega lying between 0 to pi, but the group delay we had seen is greater than or equal to 0. So today in fact we have also seen a couple of times in the previous lectures about the minimum phase systems. So okay, so first of all, the important point to note that whenever a rational function is given to you, there are two responses associated with the rational function. First is the magnitude frequency response, and second is the phase frequency response. For the all pass systems, the magnitude is always unit. So, but we also know at the same time that the frequency response magnitude does not uniquely characterize the LTI system for which some rational function is given to you. Okay. So we also need an additional response, which is the phase response, so that we can completely characterize the LTI system. So far, whenever we had discussed or whenever we had labeled some systems at the minimum phase systems, we said that all the poles and, or sorry, all the zeros of the rational function must lie inside the unit circle. So if the system is stable and causal, we know that the poles must lie inside the unit circle, right? But this stability and causality property do not put any restrictions on the location of the zeros. In one of the previous lecture we discussed about the inverse systems as well. So if we are interested in finding an inverse system, so at that time we need to put additional restrictions on the zeros, meaning to say that all the zeros should be inside the unit circle if we want to compute if we want the inverse system to be stable and causal also. And that time we had labeled those system as the minimum phase system. But this is just one of the this is the implication of the important definition of the minimum phase system. We have not yet seen the physical significance of classifying any system minimum phase system. So the discussion on this minimum phase system would be divided into two parts. So first of all, we see the decomposition of any rational function, and this decomposition would be in terms of minimum phase system and all pass systems. So initially we shall start that all the zeros, if all the zeros of a rational function are inside the unit circle, then it is a minimum phase system. And then we shall see that the second topic, what we will see about the frequency response compensation of non-minimum phase systems. And then finally at the end we shall see the physical significance or the definition, a proper definition for a minimum phase system in terms of computing the phase of the systems. Okay, so this is a generic about the minimum phase system. Let's see the decomposition. Okay, so any rational function, let's say any rational function is given to you h of z. We can always decompose this h of z as the multiplication of two rational functions, where the first rational function would be uh, a minimum a function which has a minimum phase, meaning to say that all the zeros of this h min would be inside the unit circle multiplied by all pass z. Okay, so this is an all-pass system, and this is a minimum phase system. Okay, so we shall restrict our discussion to only to stable and causal system, but this decomposition generally applies more generally otherwise. Okay, so the first factor is the minimum phase system, and the second factor is the all pass system. So any rational function h of z you can write as a multiplication of h mean and hap. Now let's try to understand by a couple of examples. Let's say your h of z is given as some function h1z and multiplied by a polynomial of z, it is z inverse minus c star. So c star is a complex number, and in c star denotes the c is a complex number and c star denotes the complex conjugate. Okay, so this polynomial, you see that it contains a 0 which is outside the unit circle. Okay, and the 0 is located at z is equal to 1 upon c star, where mod c is less than 1. So if mod c is less than 1, then the 0 is located outside the unit circle. This h1z is some rational function which collects all the remaining poles and zeros. Remaining poles and zeros are inside the unit circle. Okay, and let's call it, which would be a minimum phase system. But still, you see, although it is a minimum phase system, the second factor is not an all pass system because the magnitude is not 1 of that system. So in order to put this as the above equation, we write the equivalent representation of this h of z as hz by, because h1 of z is already a minimum phase system, and here we multiply with another polynomial 1 minus c z inverse, and we put z inverse minus c star divided by 1 minus c z inverse. Okay, so what do you see here? That we have introduced this factor in the rational function h of z. So we know at the outset that this can be cancelled out, and after cancelling this factor, the remaining part would be the same as hz. This is an equivalent expression, but now we shall see that how it can be classified as the minimum phase system and the all pass system. So you see that this is a minimum phase system because we know that mod c is less than 1. So we have already seen that all the zeros of this h1z are inside the unit circle, and the 0 here would be located at z is equal to c, and since c is less than 1, so the overall zeros of this rational function will be inside the unit circle. Okay, now the second factor, which is this one, and this one is an all pass system. If you see the previous lecture, this is the same representation we have used for defining the all pass systems, right? So this above example can be generalized to include more zeros which are outside the unit circle. But the basic idea, what you should understand, that in this particular equation, that we have h main which contains all the poles and zeros inside the unit circle. Why I am including poles? Because we are limiting our discussion to the stable and causal system. And this h pass contains all zeros of h of z that lie outside the unit circle together with the poles to cancel the reflected conjugate reciprocal zeros in h main. Okay, let's see that this we have defined as h min, and this we have defined this as HAP. So what happened here, that whatever the zero we were having outside the unit circle, we have reflected its conjugate reciprocal 0 in h min together with the pole in all pass system. So this is just a reflection, because this reflection would be useful when we discuss about the compensation, right? Let's see one uh, quick quick example again. So here your, let's see, and you are given h1 of z as 1 plus 3 z inverse and 1 plus 1 by 2 z inverse, right? This is one rational function. So you see the pole of this h1 of z is inside the unit circle. So it has a pole inside the unit circle at z is equal to minus 1 by 2, and it contains a 0 at z is equal to minus 3. So it is outside the unit circle and it's a non-minimum phase system. So we need to choose the appropriate all pass system to reflect this 0 inside the unit circle in h min. Okay, so if we use the above formula where we had seen with C, so here clearly you have C as minus 1 by 3. Okay, so putting this C is equal to minus 1 by 3, which is the reciprocal of this thing, then your all pass system would be given as Z inverse plus 1 by 3 and 1 plus 1 by 3 Z inverse. Okay, and your H min Z would be your 3 times 1 plus 1 by 3 Z inverse and 1 plus 1 by 2 Z inverse, right? Because this, if you put these two functions in multiplication, then this factor would cancel out, and this is the factor, the reflection of the zeros which were 0 which was outside the unit circle, right? Now let's consider a higher order system, or higher order in the sense, meaning to say that if you contain two zeros and it's a complex conjugate pair, let, uh, let's consider another function h2 of z as 1 plus 3 by 2 e raised to the power j pi by 4 z inverse and 1 plus 3 by 2 e raised to the power minus j pi by 4 and z inverse. Okay, and you have a pole which is inside the unit circle. So you see clearly that this H2Z contains two complex zeros which are outside the unit circle and a real pole which is inside. So first of all, I will factorize this to take 3 by 2 common, or let's say by factoring this term and this term out of the numerator terms. And once I take out these two terms, I would get 9 by 4 z inverse plus 2 by 3 e raised to the power minus j pi by 4 and z inverse plus 2 by 3 e raised to the power j pi by 4. Okay, 1 minus 1 by 3 z inverse would stay as it is. Okay, now here we again see in terms of the above formula where C is this part. So we can write h2 of z as the multiplication of the minimum phase rational function and an all pass rational function. So the minimum phase rational function would be 9 by 4 1 plus 2 by 3 e raised to the power minus j pi by 4 z inverse, and 1 plus 2 by 3 e raised to the power j pi by 4 z inverse, divided by 1 minus 1 by 3 z inverse. So this is the minimum phase, and the all pass would be your z inverse, the zeros which are contains the zeros which are outside the unit circle, plus 2 by 3 e raised to the power minus j pi by 4, and z inverse plus 2 by 3 e raised to the power j pi by 4, divided by the factors which cancel out the zeros in the minimum phase function, 1 plus 2 by 3 e raised to the power j pi by 4 z inverse, and its complex conjugate 1 by 2 by 3 j pi by 4 z inverse. Okay, so this is how you can write for the higher order systems as well. Okay, so this is about the decomposition. Now what is the use of this decomposition? When we talk about the frequency, we shall see it in the frequency response. Compensation of non-minimum phase systems. Okay, so let's see one of the scenarios, and this was one of the motivations also when we discuss about the inverse system as well. Let's say you have some sequence S of n, okay, which you want to transmit over a channel, okay, and at the other end you receive the signal, let's call it SC of n. So whenever you transmit a signal S of n to be received at the receiver end at SCN, the ultimate objective is that you want that your S of n should always be equal to SC of n, meaning to say that your signal should not be distorted at all in terms of the magnitude and in terms of the phase as well. Okay, but this is a very idealistic scenario. Generally, whenever you pass a sequence or a signal S of n over a communication channel, there is always some system, what we call the distorting system. Let's label them as HD of Z. Okay, and your distorted signal is your SD of n. Now, since we want SC of n is equal to S of n, then for that we put a compensating system. Let's label them as SC of Z, so that we can get S of n as SC of n, right? Now this HD of Z is the system offered by the communication channel many times. So if HD of Z, okay, let's write this, the overall transfer rational function is G of Z, which is basically the multiplication of HD of Z times HC of Z. Okay, now if your system HD of Z is stable and causal, right, and your HC is also some stable and a causal system, then perfect compensation is possible only if HD is a minimum phase system, so that it has a stable causal inverse, because in that case we can put SC of Z as the inverse of 1 upon HD of Z. So it is like computing the inverse response of the distorting system. Now, the distorting system is stable in causal, and its inverse, which is Hc of z, to be stable in causal, it is only possible if you have Hd, a minimum phase system. But this is like I said, it's a very idealistic scenario. You cannot rely on the communication channel to be stable in causal, and its inverse to be stable in causal as well. Meaning to say, it's a minimum phase system, right? So now we shall see that how we can use the decomposition, what we have just introduced, in order to construct a compensating system Sc of z. Because if your Hd of z is a non-minimum phase system, meaning to say that the zeros are outside the unit circle, then you very well know that if you compute Sc of z using this expression, then the zeros of Hd of z would become the pole of Hc of z, and the poles in that case of the compensating system would be outside the unit circle, and it's an unstable system. So the output or Sc of n would reach to infinity, irrespective of whatever is your SN signal is. Okay. So we shall now use the decomposition technique to see how we can design this Hc of z or construct this Hc of z. So let Hd of z is known or approximated rational function. Okay. And it can be decomposed as Hd of z, Hd min of z, and HAP of z. Okay. So now here, instead of with the help of this decomposition, now instead of taking the inverse of the overall function, we shall construct Hc of z, the inverse of only the minimum phase system, because for those system we are sure that the poles of Hc of z would be inside the unit circle. Okay. So substituting this Hc of z into this expression, what you will get? Gz as Hd, we can write this Hd min of z, and HAP of z, right? And Hc as 1 upon Hd min by z. So you see that this vector gets completely cancelled with this vector, and the remaining part is HAPZ. So Gz is in fact becomes an all-pass system with the selection of this as a compensating system. So the outcome of this compensation is that the frequency. So note that. So let's write me concretely that the outcome of what we have just seen is that first of all, frequency response magnitude is exactly compensated. Right? But still the phase response is modified to the contribution made by the HAP of e to the power j omega. Right? So at least we are sure that given if Hd of z happens to be a non-minimum phase system, at least the signal or the receiving signal won't be reached to infinity, meaning to say that the internal system is a stable system. Okay, we can see one example for to visualize all these scenarios. So compensation of an FIR system, that is finite impulse response system. So let's denote the distorting system as 1 minus 0.9 e raised to the power j 0.6 pi z inverse 1 minus 0.9 e raised to the power minus 0.6 pi z inverse multiplied by 1 minus 1.25 e raised to the power j 0.8 pi z inverse and its complex conjugate polynomial 1 minus 1.25 e raised to the power minus 0.8 pi z inverse. Okay. So in this HD of Z, you only see the zeros because all the poles are located at the origin. That's why we called it as the finite duration impulse response, because it only contains the zeros. Otherwise, all the zeros are at the origin. So the system is stable because all the zeros are inside the unit circle. And HD of Z, like you were saying, is a polynomial with only negative powers of Z. So the system is causal. So this system is stable and causal both. Right? Let's see the pole zero plot of this system, which is given by here. So in this pole zero plot, what do you see? That all the zeros, poles, which is a fourth order pole. So there are 4 poles which are located at the origin, and there are 4 zeros, and out of those 4 zeros, 2 zeros are inside the unit circle and 2 zeros are outside the unit circle. So it's a non-minimum phase system. Right? Now we shall visualize the the 3 main plots: the log magnitude plot, phase plot, and the group delay plot for this system HD of Z. Because seeing those plot, we will plot uh, for 3 rational functions. First of all is HD of e to the power j omega, HD. Another is HD min, so that you can see that how the all these 3 plots looks like, and finally for the HD of AP. Okay, so let's first of all see. So these are the frequency response for FIR system. Uh, the first one is the log magnitude plot. Okay. The second one is the phase response, and this phase is of the principal value only. Okay, and this is the group delay. Okay, so this is of the HD of Z, HD of e to the power j omega. And since in your tutorial classes where you have discussed the MATLAB based exercises, you can use those functions to plot these curves by yourself as well. Okay, so this you can do straightforwardly, right? But seeing these plots is not of much interest to us. We are interested in mainly the plots of the other 2 functions, the minimum phase system and the all pass system. So for these are the 3 plots for the minimum phase system. Okay, this is for the HD min. Okay, you can construct the HD, the minimum phase function. or let me write this function for you. So this HDMin basically, just a minute. So we were discussing about this initially stable and causal for this HD. So again, the zeros. So we had seen from the pole zero plot that the zeros located at 1.25 e raised to the power plus minus 0.8 pi are outside the unit circle, and we want to reflect these zeros to their to their conjugate reciprocal locations inside the unit circle. Okay, so first of all, we will take the factor 1.25 and 1.25 e raised to the power plus minus j 0.8 pi correspondingly from these two factors, and can be given as hd of z as 1 minus 0.9 e raised to the power j 0.6 pi inverse okay, and the factor is 1.25 square, and the remaining part is z inverse minus 0.8 e raised to the power 0.8 pi and z inverse minus 0.8 e raised to the power j 0.8 pi. Okay, so this would be the equivalent HT of Z. So having seen this in the similar form of the formulas we had seen earlier, I can write directly my HD min as 1.25 square 1 minus 0.9 e raised to the power j 0.6 pi z inverse and 1 minus 0.9 so power minus j 0.6 pi z inverse times, which needs to be reflected inside the unit circle, 1 minus 0.8 e raised to the power minus j 0.8 pi z inverse 1 minus 0.8 e raised to the power j 0.8 pi z inverse. Okay, and your all pass z would be your z inverse minus 0.8, the factors which contains the location of the zeros outside the unit circle is these, and the factors in the denominator which cancel out their reflection in the h min. Okay, so now we shall see the, and we had seen the all the three plots for this function. We can now see the plots for these two other function h min and hap. Okay, and this was we were seeing in our second set of plots. Okay, so the first is the log magnitude. Okay, and the second is the phase response of the principal value, and the third one is of the group delay. So here in this plot, just a minute. Okay, so in this plot, in the first plot, what do you see? That in the log magnitude, because when we would see the log magnitude plot for the all pass system, we know that it does not contribute anything in the magnitude. So the first part, the first plot of this h mean should be definitely equal to this one of the actual log magnitude plot, right? This is what we've seen. And the next one is of the all pass system. So all the properties remains valid, that the group delay would be positive and the phase response would be negative or equal to 0. Since this is a principal value, that's why you are seeing these two discontinuities. Okay. Right. So now you can also plot these figures for these three rational functions by yourself in the MATLAB. Now in the next class we shall discuss about the properties of minimum phase system, and then we shall completely define the physical significance of this minimum phase system. We shall carry forward this example. So today in this example we were just interested in seeing the plots for different functions, and we know at the outset that the log magnitude plot of the h minimum function would definitely be equal to the log magnitude plot of the overall function. Okay, so we can end here today. Thank you.